Hey everyone, so I just want to provide the quickest possible breakdown of the efficiency of the different types of electric motors. I won't cover all of them, but I will cover the most common types. So in this video, I'll start with the PSC motors, which is permanent split capacitor start, and shaded pole motors. So this one is permanent split capacitor start. It may or may not ship with its own capacitor, but in this case I had to purchase a capacitor for it, a start and run capacitor. So this is something that helps the motor to start and in some cases plays a role in keeping it running. And the shaded pole motor doesn't require that too, although it has its own disadvantages. So the efficiency of electric motors varies very widely, and that's why I feel the need to point it out in this video and to clarify the differences. So the bigger one shown here is 63% efficient, meaning it converts 63% of the energy that it consumes into mechanical energy. So that is reasonable for a small alternating current fan motor, although it's not strictly a fan motor. But anyway, so when you're shopping around in a store, unfortunately you're not going to see an efficiency percentage or rating or anything like that. However, you will see the power consumption and the power output. In this case, this 230 volt motor draws 1.7 amps, and at the maximum load is 2.6 amps. And I should have pointed out by the way that it's up to 63% efficient. And yeah, the horsepower is 1/3 of a horsepower. So to convert that to watts, you can divide 1 by 3 and then multiply it by 745, because 1 horsepower is 745 watts and then a little bit. And this motor now, a significantly smaller one, 1/20th of a horsepower. This one is 115 volts and 2.1 amps. So this is a less efficient one. This is 15% efficient. So 10 to 20% efficiency is typical for most shaded pole motors. Some are actually less than that, but it's typical. So shaded pole motors are known for being very simple. Both of these are alternating current motors. Shaded pole motors are known for their reliability and their simplicity. Right? There are no brushes. The first motor shown doesn't have any either, but there are no brushes and no capacitors required. Also, brush motors are usually of the universal variety. They're usually called universal motors. The efficiency of those is often in the 40% range, and the brushes do wear out after a while, so that's a disadvantage as well. Those motors tend to be noisier as well, extremely noisy actually. So those motors are frequently found in vacuum cleaners, washing machines in some cases, and what else? Leaf blowers, that kind of thing. Anyway, so right, as I was saying, you can calculate the wattage using the amperage and the voltage, and then you can then use you can then divide the wattages by each other, the output and the input wattages, and then that will give you the efficiency. So aside from that, there are some other notable differences. For example, this bigger one uses ball bearings. Ball bearings don't use friction. That provides an efficiency benefit as well, and they are a little smoother, meaning less bearing noise. This is a sleeve bearing motor, so it doesn't roll. The bearings rub, against the shaft as it turns. So I wish I could provide you with a clearer view of inside these motors, but I don't think it's going to be feasible right now, since I don't really have a proper mount for this camera, and I have to just hold it in my hand, unfortunately. I might be able to give you a better view of inside of this one though. Not much to see there, just poles, rotor, etc. Alright, so both of these are commonly used in, mostly used in air conditioning and refrigeration applications, and because of the highly standardized nature of air conditioner fans, you can usually find a more efficient replacement for whichever fan motor you're replacing in an air conditioner. So for example, if you had this motor in an air conditioner and it went bad and you're replacing it, you can actually find a PSC or permanent split capacitor start version of it too. For example, okay, I don't remember the model number, but there are other models which are significantly more efficient, well over 40%. So you could easily use less than half of the power that this one consumes without reducing its power output or performance. So you can do that without any ill effect. How much it costs, well, that varies as well. Some are expensive, some are actually quite affordable. So this is a condenser fan motor, and these are frequently used in freezers and refrigerators for the evaporators. So that wraps it up for the AC alternating current motors. And DC motors are a little more, what's the word now? Are a little different, because electric motors internally they alternate current. They need alternating current because it's just how they work. So that's why alternating current motors they're actually easier to make them. It's easier to make brushless versions of them because of that. DC motors, on the other hand, may have to be electronically commutated. So I don't currently have any DC motors nearby to show you. There's nothing to see anyway because they're sealed. All of mine are sealed at least. But DC motors are more likely to be brushed. But whether they're brushed or not, oh, by the way, I should have pointed out, brush motors are less efficient than brushless motors, whether they're AC or DC. And also, so electronically commutated motors tend to achieve a very high level of efficiency, often over 80%. Some of them even exceed 90%, but not usually though. So whether they're AC or DC, for example, 3-phase motors, whether electronically commutated or not, can exceed 90% efficiency. So they're, at the top of the game in that regard. And brushed DC motors can still achieve over 75% efficiency very easily. So they're capable of getting the job done efficiently as well. But they have their own disadvantages because electronically commutated motors are very expensive to manufacture and very costly to replace, and they're more likely to be non-standard. The units that use them, I'm not sure why, but that's the unfortunate disadvantage of them. So I hope that helps you when choosing your next electric motor, whether it's a fan motor or even for any other application. It doesn't matter if it's for a fan or not. You can always just look at the label in the store, make your calculations to determine how efficient it is, and then pick the most efficient one. And surprisingly, you often can get a more efficient one for the same amount of money. So it's not like you be emptying your pockets. So yeah, sometimes there's nothing to lose in that case. Anyway, thanks for watching.